for the universe as a whole, and for subsystems of the universe that get more or less isolated from the rest of the universe. And the argument for that is a bit detailed. It's written here. I'm not going to go through it. So the argument for why it is that the universe, that the entropy is increasing since 13.7 billion years ago, that's sort of obvious if the entropy was so minute because of the universe being so densely located, so gravitation not playing a big role. Oh, I should explain this a little more. Most of the entropy of our universe comes from the role gravitation plays. And so there's something a little counterintuitive about this. It's the more or less uniform distribution of matter in the early universe that makes for a very high entropy, whereas, so it makes for very low entropy, makes for very low entropy, whereas we think that uniform distribution of particles in gas make for high entropy. Both of these are right incompatible claims, but gravitation is such an overpowering element in the universe that the uniform distribution of gravitation not yet playing a role at the beginning of making matter clumping. As matter clumps, entropy increases. The entropy due to gravitation increases. So in any case, there's a line of argument that leads to the conclusion that if the entropy was very tiny at the Big Bang time, some physicists and cosmologists have calculated how tiny. Roger Penrose, in a book of his, actually, where I saw it, but other people did this, I think, before him, actually gives what he thinks is the value of the entropy of the universe. Very small. It's still small now, incidentally, compared to what it could be in what's called equilibrium. But it's much bigger now than it was then. And it's pretty clear how if it's very small, and if almost all states are increasing states, as Boltzmann showed, then it makes sense that the entropy of the whole universe would be bigger now. And there's a line of argument that if you take a system like a pail of warm water and you put an ice cube in it, you put it in the corner of the room and don't bother it, so nobody's interacting with it, you're not putting it in the refrigerator, or ambient temperature, so it's constant, why it is that the ice is very, very likely to melt as its entropy, and why its entropy will increase. So I sort of give this argument this page here. So here's a solution now to Boltzmann's problem, and it also turns out to be a solution to the aberrant state problem. So it's a solution to the hard problems of physics, the hard problems of physics. And that is introduce this past hypothesis and the probability distribution. Oops. Okay, so this is now what I call the mentaculus. What David and I call it the mentaculus. Now this is so ridiculous, why we're calling it the mentaculus, that at some point we're going to have to stop saying it. But I know some people here know, because I know me. So I'll explain it. So there's a movie by the Coen brothers, who happens to be a favorite of David and myself. I know somebody who knows Joe Coen, and I've been promised that I will get to meet him, and this would be like a great thing. He lives in the Upper West Side, but I haven't ever met him, but I have seen his movies. So one of his movies is called A Serious Man. You might have to have a certain kind of ethnic background to really appreciate this movie. Some people have seen it, yes. Okay, so in it, there's a kind of nebbishy brother to the main character, who kind of can't do anything right. He's not really the main character in the movie even, but he's always busy working on something when he's not getting into trouble. And so his brother, who's a physicist, says, so what are you doing? What are you working on? And he says, the mentaculus. And his brother, the physicist, says, mentaculus, what's that? He says, it's a probability map of the universe. The brother says, oh yeah, he doesn't want to hear it anymore. Okay, but what we've now said is that, look, the right way of responding to this big problem, it was the big problem, or one of the big problems at the end of the 19th century, how to reconcile macro thermodynamics with fundamental classical mechanics. The right way to do it is to introduce a probability distribution, as Boltzmann thought, a uniform distribution, but you you've got to introduce it at a particular time, namely a time when the entropy of the universe was very tiny. Now you have something like a complete theory of the world, given the dynamics too. And we don't know exactly what the right ontology of the dynamics of our world is. But here's a bet, that whatever it's going to be, we're going to need something like this in it too. There are some ideas about how you might do it a little differently. Colleague of ours at Oxford, David Wallace, has a somewhat different idea about how to do it. But it basically comes down to something that is good. What's amazing about this, what's philosophically breathtaking about this, if you stop and you think about the ambition, is this means that there's a probability distribution over all possible physical trajectories, physical histories of the world. But that means there's a probability distribution over all propositions that are made true or false by physical histories of the world. And if you're a physicalist, you think that that's all propositions. Now there's a technical mathematical thing here because of infinities. If somebody, it's in somebody's mind, let's save that for the discussion, okay? It really doesn't affect the philosophical point. Is the picture getting a little bit, the ambitious picture here somewhat clear? Maybe this will make it a little clearer. The claim is that to solve the right way Boltzmann's problem, you have to introduce an objective probability structure to the whole world, all the possible ways our world might be, as long as it has more or less our laws, as long as it's a world in which entropy, second law of thermodynamics works. That's probabilistic form. And in fact, this can be kind of pictured. Now this picture isn't exact because I'm inept at making pictures. If I was a little bit better, the picture would be a bit more complicated. But this will give you the basic idea. Think of the very thin lines as representing possible micro-histories of the world. Those are deterministic on the classical mechanics that we're thinking about. I should also add that some of the better ways of thinking about quantum mechanics also turns out to be deterministic. We can say that for the workshop too. But if you're a realist about quantum mechanics, you're basically going to hold it as deterministic. There's only one realist kind of account, which is really probabilistic, and it also fits in with this picture quite well. Again, for the question session, we can talk about it. So the thin lines represent micro-histories of the world. Given the exact micro-condition of the world, I don't give it in here, right? To write it down. Nobody can write it down, needless to say. But given it, as Laplace says in his famous remark, about Laplace's demon, superintelligence, given it, everything else is determined. Okay? Again, there's some fine points to it. That's the micro-history. But what about the macro-history? Well, I've been introducing this word macro without defining it. Because the reason for that is that exactly how you characterize macro is not going to make much of a difference here, I believe. But macro is basically sort of saying, not very tiny volumes of the world, what's going on, what the temperature is, and if you divide the world up into 1 cubic centimeter parts, say what's going on in that, what the temperature is in that 1 cubic centimeter part, what the average frequency of radiation is, what the density of matter is, and so on. Now, in fact, 1 cubic centimeter is way too big. You can do it for very minute things, as long as it's not like absolutely micro. And you will get this, with that kind of a division, you'll get this kind of a picture, where you get what looks like indeterminism in the evolution of the macro state. People know this in popular science stuff from, little things that from what I said at the very beginning of this talk, we've introduced it. Just think about all the funny little things that happened that brought us all here. Little changes. A butterfly flaps its wings in South America, and sometime later, a hurricane hits someplace in North America. Okay? These little things that we know about make for big differences towards the future, we think, but not towards the past. Well, this was, I think, is a consequence of the mentaculus. I'm going to try to explain why in a minute. Okay, but here's the thing that's breathtaking. That if this is right, then solving the hard problem of physics in this simple way leads to a probability distribution of everything.